Okay, so I would like to welcome Ömür Arslan for our, I think, third or fourth ROMER Talks guest. He's an assistant professor in the Department of Mechanical Engineering at the Eindhoven University of Technology in the Netherlands. He received his PhD in Electrical and Systems Engineering from the University of Pennsylvania in 2016, and BS and MS degrees in Electrical and Electronics Engineering from Middle East Technical University in 2007 and Bilkent 2009. His current research focuses on the algorithmic foundations of robotics and aims at systematically integrating perception, control, planning, and learning to achieve safe robot autonomy in dynamic environments. His research interests include robotics, motion planning, multi-robot systems, sensor networks, machine learning, and machine perception. Today, he will be talking about so the challenges and hopefully some solutions on to how autonomous robot motion design can be certified for safety, if I understood correctly from his abstract. So with that, without further ado, I would like to leave the stage to Ömür. Ömür, the stage is yours. Thanks.
Thank you very much, Erol Hocam, for the introduction. It's really nice to see very familiar faces from my time at METU. It has a very special place for me, and it's good to see people from the minor program I had at METU in addition to my major program in electrical engineering. Actually, I studied mechatronics with Burak Oku, and there are many other people also from Robotics Society at METU. So all of these people have some influence on my, professional development. Of course, I don't know if Umut Saranlı and Avşar Saranlı is also here, but they are definitely, had significant influence on my professional growth as a mentor, as a supervisor during my master studies, also at Bilkent University, especially with Uluç. And today I will partially mention about some of the work I do on feedback motion planning, and I will have some arguments about the safety certificates, how they are critical for robot motion design. And I'm currently an assistant professor at TU Eindhoven for the last 2 years, and it was a little bit challenged during the pandemic, but things are getting better. Hopefully I will be able to tell more next time with more experiments and so on. But today it will be more like intellectual discussion with fundamental, questions about reliability and dependability in robotics. And I believe that I don't need to convince anyone here about how important robotics is and how they are, getting more and more involved in our daily life, from autonomous mobile to household events, and especially maybe logistics settings, assistive robotics for the elderly. So I think what makes robotics that attractive, of course, some maybe financial, business plans for the industry, but from my perspective, the one unique capability this technology provides, and no other technology was able to provide before, is the autonomous motion. And of course, that comes a little bit, different challenges, because robotics first applied in very structured industrial settings, and it was relatively easy to maybe implement, and there was less concern about dependability, because now we are talking about robots. They come from the structured environment to unstructured setting, where they need to work around people, around other autonomous vehicles. And when you think about this problem, it's a little bit challenging, because when you just think about interacting or designing some, autonomous motion around another autonomous device, especially if you don't know anything about how it perceives the environment, how it plans, it's a big challenge. So it is completely different than a kind of a centralized multi-agent, system design approach. We need to be able to deal with all the ambiguities, uncertainties, and unknowns in the environment, in the behavior of the both people and these, autonomous systems. And I think this autonomous motion comes with a unique challenge, and I'm very interested in that part, how we can ensure the safe autonomy for such robotic systems so that we can reliably deploy them in practice around people, or when we send them a mission in the Mars, they should work as they are planned. So we should verify the expected motion. So of course, in the lab, we are not gonna be able to do all of this. A little bit, to give you some idea what kind of infrastructure we have at TU Eindhoven. I'm mainly focused currently on mobile settings, small-scale vehicles with onboard perception and decision-making mechanisms. So they are scaled cars, maybe small, mobile platforms like turtle boats, and I use them for both research and education, because the other aspect of robotics, I believe, we can have all the hardware you want, all the sensors, but the work is done with people. And being in the academia, I believe that is the privilege, to help those people to really grow as the future engineers, roboticians that can contribute back to that literature. And in addition to motion planning, I'm also very interested in the mobile perception, because from my perspective, in order to really achieve true reliability and dependability in a robotic platform, you need to integrate both perception and motion all together. So from my perspective, I am not looking for developing a new perception algorithm, new localization or mapping algorithm, but more interested in the quality of localization, quality of the mapping, so that I can combine and reuse that information when I am designing a motion planning algorithm. A motion planning algorithm that can help the perception. When you are driving around, maybe you sometimes need to slow down because your localization, your visual odometry, maybe it gets worse. And if you can monitor the help of these perception algorithms, you can reuse this information back in your, motion design. I also look from different source of information when you are designing the such complex robot behavior. Onboard perception is important, but I also think that external perception, like in this figure, you see a security camera, it can monitor the motion of the robot and provide a side information. And it's very critical when you think about the traffic monitoring setting, because your car approach with autonomous driving mode intersection, it cannot see everything, but side information coming from the security cameras, traffic lights, they can help us to increase the safety of the overall system. And another example, maybe in indoor setting, you have a cleaning robot, a Roomba. It's very small, doesn't have much perception skills, but a security camera placed in the same place, in the same house, for monitoring how the elderly maybe does, or for security purposes, can it provide, useful information for better process of these, vacuum, these kind of interesting challenges we look at in my lab with the students. But today's topic is the safety certificates, how we can guarantee the safety of my robotic system. And especially I think that these elements are very critical for the motion design. So if you have any question, by the way, please share on them in the chat. I won't be able to see them mostly while I'm talking right now, because I am very unexperienced with Zoom, but I will have a second screen to check if you have any question. And I plan to address them at the very end. And we will also have an open discussion about this. So going back to the motion planning task, from my perspective, you may have a mobile platform on the ground or flying or swimming. So you want to go from start to goal, and you have some environment, there are some constraints, some content, maybe you want to avoid collision with some buildings, but also avoiding collision with people are completely different tasks. And you want to build a plan that will take you from start to goal. This is the motion planning. And when we think about the safety, it can have different interpretation. Given a motion design, you can check if this motion is, safe. And from my perspective, this is not a safety certificate for motion planning, but it used the motion plan in a kind of a naive way, perform some collision detection along to maybe the determined motion, and you just want to verify, is this plan is safe? But I am more interested in how to design informative safety certificate that will support the motion planning task itself. And from my perspective, it's not just being able to check along this motion, do you have always a collision-free position? More than this, safety certificate should relate back to the environment, if possible. I will give some example during the talk how it can be done, maybe better than just doing the collision detection. It should be able to relate back to the motion of the robot, so equation of the motion of the robot itself. Maybe also you may be using some certain trajectory representation to design some closed loop motion, and then I think that a safety certificate should be also relate back to that trajectory representation if possible. And to give you a kind of a toy example, to generate such a trajectory, a common approach, maybe a standard approach, is you can look at some safety corridors along this environment. So it's built based on the environment information, completely ignoring what kind of platform maybe you are designing your motion. And then you can try to optimize a trajectory along these, corridors, because you know that it's safe, and then you can find your solution. But the problem is it's lacking at the beginning, it's lacking the information about the robot itself. You created a corridor just using the environment information, but you ignore the equation of the motion of the robot. And why to have just finite cover of the environment? Maybe it is a better approach to have a continuous varying of these safety corridors if possible. And there are many, elements here you can really critically approach and try to do something more than a collision detection, but a tool that will help and support the motion planning task. So from my perspective, one of the first thing when I look at a safety certificate is it should inform the robot about its environment, surrounding as effectively as possible. I think it's maybe very, intuitive, very obvious. All of us think that, yes, this should be there. But when it comes to applying such a safety certificate or finding one, unfortunately, we don't have much of such tools available yet. So there are more new tools, but when we look at the classical way of collision checking, they are very primitive when it comes to informing the robot about the environment. And what does it mean? So again, let's look at an example. We can think about the circular safe zones around the robot. So you have a robot moves in a cluttered environment. Legs are the obstacle you want to avoid, and blue is your robot location. And a classical way of defining a safety zone around the robot is look at the largest circle that is free of collision. So it is the yellow one, and you can also decrease the size by the robot body size so that the center location is free to move in this green region. So from my perspective, this is a very primitive construction because you lose lots of information when you go from this environment to green region or the yellow region. You end up with a very symmetric information. You just tell that what is the distance to collision. It reminds me a game, kids plays a lot, this hot or cold. So it's a simple game, hiding game. So you are hiding something from your robot, and that is the information about the environment. And when we look at a similar environment, actually, we usually have a sensor that tells significantly more about the local, geometry. So you can think about the laser footprint. This can be one information, but do we also want to give so much detail, so much, detailed information for encoding collision. Maybe it's also too much, this red footprint compared to the yellow region here. And from my perspective, the relation between these two, the intermediate level, maybe instead of just looking at the very closest collision, look at all the critical collision points. And how I define the critical collision points is all the local minima in the range data. They are somehow describing the critical collisions associated with the convex obstacle shapes around you. So when you look at these local minima, it automatically related with some kind of, convex decomposition of the environment into the convex obstacles, and you pick the closest collision from all these, potential convex regions. And what I suggest is maybe between the robot body and the obstacle, use a separating hyperplane like in the support vector machine, so that you can construct a asymmetric and safe region around the robot. I call them support safe zones, like the support vector machines, because this region, yellow, is actually linearly separated from the obstacles based on this supporting vector field, the supporting vectors. So these are linearly separated between the yellow region and this critical collision points you see in this range data. And I think that this is a kind of a nice capture of the local geometry. It's not as detailed as the red region here you see. And the other problem with the red region is it's non-convex. So there can be other artifacts about this non-convexity, but it's just sharing this convexity property with the circular one. And compared to the circular safe zone, it captures the local geometry up to a certain level, not as detailed as the red region. And this can we use such a construction for safe navigation. And by using a simple idea, something like, you have this safe zone around your robot, you have a destination to go, you can pick the closest point, and you can continuously move towards that closest point and expect that maybe you will reach the destination. It's like chasing a carrot on a stick. And when you move, the location of the local goal changes based on where you are in the environment. So the way you encode the safety now supports the motion planning, and it also reflects the environmental property when you are making a decision. And when we apply this to the robot platform, like differential drive, you see that it can detect the local obstacle using the laser scanner, use these critical collision points. These are the local minima in the range data, construct these local safe zones, and reactively reach the destination. And why I call them reactive? Because actually we didn't plan any path. We just construct a nice vector field, a feedback policy to reach. So if I took the goal and start moving around, it will just change its behavior reactively. That is a kind of a very simple combination of the sensory information with the action. And here, the way of defining, how we can encode the collisions, it helps us with the motion planning. Because if you apply the same procedure with the circular safe zone, basically you cannot get much out of this kind of, policy. It will get stuck at these local, minimas, undesired local minimas. So this was the one demonstration of why informative safety certificate may play a critical role in autonomous motion design. Of course, you are not only limited to such, a relatively simple environment. You can apply the same idea with probabilistic motion planning. Now, instead of straight line steering, which is very basic approach in probabilistic motion planning, when you have sample start and the goal configuration, you try to combine them through the straight line. And what we suggested before is, we can use these local support zones and then have a motion primitive sensory steering primitive that will adjust the steering direction and steering step size on the fly adaptively. And all of a sudden, what you obtain is when you apply a PRM like probabilistic road maps, you increase the connectivity or your network. On the top right figure, you see a PRM with straight line steering. We just change how the local connectivity is defined. Instead of the straight line steering, we use this policy on the left, and the connectivity increases significantly. And actually, one of the promises of this method is you can plan very effectively around narrow passages. And this is a known problem with the probabilistic motion planning, because you need to effectively sample there around these narrow passages, or you need to find a way of, informing your steering mechanism around these narrow passages. And I believe that this is nothing but really encoding the collisions in a proper way so that you can capture the local geometry and use that back for motion planning, not only for safety verification. So here on the top, you see that the algorithm doesn't able to perform well because it was basically using the straight line steering, and the collision checking is like yes or no. It doesn't use any geometric information about the local structure of the configuration space. And maybe another example, especially to highlight that why we need to put these separating hyperplane in a balanced way between the obstacle and the robot body is, it becomes more clear when you have the multi-robot configuration. You can apply the same procedure. You may have multiple robots with different sizes, and you can apply the separating hyperplane between them and obtain some safe zone for each robot. And you can say that whatever problem you are solving, you can try to solve that over these, relatively available regions. So some of the robots will have more room to maybe change their position and create aggressive motion, and some of them might have very small domain to change their configuration. And we applied these kind of ideas for coverage control on multi-robot setting, and we observed that sometimes, for example, some of the sensors might become redundant, so they are not participating in coverage anymore, but we can do with them. Just go to the center of their safe zone, because it's a kind of a balanced strategy. And at the end, this also helped them to find an open region to cover and become a little, again, active in the coverage. So it was, again, an unexpected behavior emerging from this kind of, if the safety is very aligned with the environmental information, in this case, the interaction between the robot, it might help the control and planning. So this was the first part of the talk. So now we will switch to another perspective. When I think about the safety certificate, the other thing I expect from this tool is it should be very aligned with the robot motion itself, because I'm designing a safety certificate for the robot's motion, not robots, body shape or other thing. Robot won't be stationary, it will be moving. So it should take into account the motion itself. Again, it can be very obvious, but at the end, when we look at the literature, we are not there yet to have very promising safety certificate. They are effectively taking the robot motion into account. And what does it mean? So when we look at the planning that also based on this control, we usually use the set invariants like Lyapunov method. So they try to use system energy or a form of potential function to avoid from collision. So from my perspective, these tools are really not designed for encoding collision. They were designed for proving stability. And like maybe 30 years ago, 1986, when first time the potential fields are applied for robotics, for obstacle avoidance, they were promising. But now we need to look from a different perspective. And for me, invariance to be or not to be is a fundamental question right now. And to give an example, I currently look at some fully actuated systems with proportional higher order derivative control. To make it more concrete, maybe for you, PD control. So you have a force control system. It's controlled based on the position and the velocity error with proportional control feedback. And you can think about the extension of this to higher order system, because when you want to apply this to non-holonomic system, dynamic feedback linearization becomes promising, and it usually yields such system behavior, closed loop system behavior, or the differential flatness for a drone. So at the end, a drone motion becomes smooth enough dynamical system behavior instead of considering the non-holonomic constraints from very beginning. So when we look at such a system stable around the origin, Lyapunov ellipsoid describes the future motion very well. So there is no problem about that. They capture really how the system will behave in the future, as seen in this animation once again. But the problem with these methods is in the right figure, you see different initial conditions, position, and the velocities. And the common thing is they all share the same Lyapunov level set. So whatever initial condition you pick, the motion prediction is the same, but the motion is completely different visibly. And one thing why we like Lyapunov-like methods is they easily generalize higher order systems, sometimes non-holonomic systems. That is the reason why we like it. But at the end, again, for very different initial conditions, it captures the motion in one way or another. But from my perspective, it is not accurate enough. It's not descriptive enough. And recently we developed some new tools like Vandermonde simplexes. It's able to capture the robot motion very accurately. So it is based on, strongly depends on the robot state, initial state, not just the the energy of the system. And what we see is for the same initial condition on the left, you see we can capture the expected robot motion much more accurately. And the closed form solution is available. So that is another maybe attractive property of these Vandermonde simplexes. And it's very intuitive. At the end, the motion is described with respect to origin by your goal, origin, your current position, x0, and an offset from x0 with your velocity. And if you go with the higher order system, the result generalizes, and you see that acceleration becomes again important in deciding the motion, and you can go even higher order derivatives. And at the end, compared to the Lyapunov invariant set methods like Lyapunov ellipsoid, we are able to capture the robot motion much more accurately. And I believe that that is very fundamental in robot motion design, because we apply this in feedback motion planning. So we combine motion prediction with planning in a closed loop system. And my approach in this kind of setting is I want to benefit from the available planning algorithms. So you can ignore the robot dynamics. You can assume a position or velocity field, velocity controlled robot, and design a high level planner. So based on A star or sampling based method. And the question is, these plans are usually not time parameterized. They tell how to go from start to goal, and you need to apply this to the higher order system you have. And usually also stabilizing your system around the set point is also a relatively well established thing for many existing robotic platforms. So to make this link between them, we use the reference governors as a planning control interface. Basically, it takes the reference plan and puts a dynamical information, some time parameterization, a dynamic time parameterization on this based on the expected robot motion with respect to this governed plan. And we use this motion prediction like maybe a Lyapunov-based motion range estimation or the Vandermonde simplexes, and we can encode the collision not just based on the what is my current position, but what is the expected motions distance to collision, and the safety level is reused in the reference governor to tell how fast you need to follow this reference plan. So this introduces a kind of a nice bidirectional interface between the high level planning and the low level control, so that you don't need to replan. You can make sure that your actual system can realize the plan as accurately as possible. And here I want to show an example of this. And before that, I need to just introduce a couple of things to understand these plots much more easily. So we have a reference plan. It is the red piecewise line here. And we create another vector field around this. You can consider that this is the velocity field for our governor system. And governor is denoted by this green. It is nothing but a virtual robot platform, just velocity control, so that I can apply this reference plan directly on it, but depending on the different time parameterization, based on how well my actual system blue can really track this governor in a safe way. So I will use the yellow motion range prediction to check my safety, and if it is far away from the obstacles, I will let the green one to go faster. And at the end, different motion prediction yields different motion pattern. And what we observe is, if you have a better motion prediction, of course, the robot will go faster to the destination. And again, the problem with the invariance approach is they are too conservative. They are not able to encode the collision in a proper way. So they are trying to use the equation of motion, but not really in a descriptive way. And when we look at the motion along this corridor, all the robot go along the corridor, it avoids from the collision with the side walls. So this is the misalignment between from my perspective, the misalignment between the motion prediction and the motion itself. So maybe next point is another important expectation from a safety certificate, because at the end we are going to apply these methods on a real platform, and we usually have that trade-off between the accuracy and the efficiency. And from my expectation, a safety certificate should allow us a systematic way of really trading off between the accuracy and the efficiency, instead of having a kind of a trial and error based, construction. And what I mean with this, I guess, again, an example can be very useful. We will switch from the dynamical system to Bezier curves. These are the very common polynomial curves used for trajectory representation, especially for drones. And one nice thing about the Bezier curve is you have certain control points to describe a Bezier curve, and they use certain weighting known as the Bernstein polynomials. One nice thing about them is they're all positive and they sum to 1 at the end. What you observe is this Bezier curve is nothing but bounded, a trajectory that is bounded by the convex hull of these control points. And a very standard approach is for checking safety, you just check if the bounding trajectory bound has an intersection with an obstacle or not, because your robot eventually need to perform a motion like described by a Bezier curve, but checking the collision along the entire Bezier curve can be computationally hard. And instead of this, you can check motion range estimated by this convex hull and verify the safety. A completely different way of checking safety of a system. from my perspective, if your system can realize this trajectory, it's very aligned with the motion. So it satisfies the previous requirement. But another nice thing about the Bezier curve is you can do systematic decomposition of these Bezier curves. So you can cut the curve into two. All of a sudden, you have two other Bezier curves, and the control points shrinks. That is a property of the Bezier curve, and you end up with tighter convex bonds on the expected robot motion. You can increase the segment number 3, 4, and you get better and better motion prediction. And after some time, you see that almost you are able to capture the motion itself with these, smaller convex regions, because each segment becomes a kind of almost a line. And for a line, convex hull of the corresponding, Bezier curve will be itself. And of course, the fundamental question is here, how many Bezier segments do we need in order to end up with such an accurate, motion representation? So what should be the proper number to have the decomposition so that I can accurately check the safety of my system? And maybe there are sometimes some trade-off between the accuracy and the efficiency as well, because of the computational constraint, real-time computational constraint. Maybe you are not allowed to go up to that level, and you need to stop at the middle. So we recently also look at these kind of questions, because when I look at the literature, this answer to that question is usually given based on trial and error. So people just pick 10, they see that it doesn't work for the specific Bezier curve they have, and then they increase or decrease to find the better selection of how many segments they need. And recently we look at completely different perspective, because one nice thing about the Bezier curve is we can do systematic degree elevation. So you can represent exactly the same Bezier curve with more control points, or you can also do the degree reduction. The picture with the degree reduction is not that accurate here, because if you want to represent a 5-order, for example, Bezier curve with quadratic, of course, there will be some approximation error. And it all depends on how you do the approximation. And we look at the available approach in the literature. So Taylor approximation, we all like it because locally it does a good approximation when you are going from higher order Bezier curve. Originally it's the 5th order, the black one here, and you go 1 degree down to with the blue, and the orange is the 3 degree down. So basically you have a quadratic approximation. Locally you get a good approximation with Taylor method, but away from the approximation point around the start and end, you have significant error. So least squares approach offers a better solution. So overall, it thinks that for such a Bezier curve, a linear segment, for example, will be a kind of a good least square approximation if you go with a quadratic, model. The issue from my perspective is the approximation doesn't capture the motion that's accurately. So for example, we often cannot give up maybe these endpoint requirements. So whenever I start the motion, I need to start at a particular point and I need to finish at a particular position. But least squares tries to make sure that there's a good balance of the error during the entire trajectory profile. So we alternatively introduced a different form of degree reduction recently, and it tries to match the curves at certain points. And what we get as a result is, if you, for example, want to look at how well you are encoding the collisions, basically distance to a point, based on these 3 different degree reduction methods and splitting approaches. So on the x-axis, you see how many linear segments you will use to approximate a given, nth order Bezier curve. On the left, it is the 5th order. On the right, it is the 9th order. And depending on the, of course, Bezier segment, you will, with the increasing number of Bezier segment, you will do better and better job. But when we look at these linear degree reduction methods to the linear Bezier segments, Taylor performed the worst. List is maybe, okay, reasonable, but uniform match captures the geometry well. As a result, we can capture the distance to collision, even the length of the curve, much more better than the other degree reduction method. So this was still not giving an answer to the original question: how many such linear segments I need in order to accurately approximate my original Bezier curve? And the answer came from the degree 1 reduction method, again, for this specific degree reduction approach, uniform match. So when you do the uniform match, you go from the nth order Bezier curve to n-1. And there is a difference between these two representation, and we call this the degree 1 reduction error, and it has a very specific structure. It turns out that for nth order Bezier curve, we will have n-1 critical points, maximas and minimas. And when you want to approximate a Bezier curve with the lower order, Bezier segment, actually you need to pay attention to this error, how well you can approximate this. And it structurally suggests that you need at least n-1, quadratic Bezier curve to match these maxima and the minimas. And because of the asymmetry, you need to have more. And as a result, we come up with this rule of thumb. So if you want to accurately approximate a Bezier curve with quadratic or the linear Bezier segment, you need 3 times n-1 quadratic segments and 6 times n-1 linear Bezier segment. And at the end, what it ensures is in these plots, the middle case, which means that independent of the degree of the Bezier curve, you get like 10 to the -3 approximation error, which is usually an acceptable approximation accuracy when we think about, how well our distance to collision prediction should be, accurate. So, of course, you can do different ways as well. You don't need to fix the number of segments always. Sometimes it's needed for, systematic optimization. But if you want to do in an adaptive way, Bezier curves also comes with another nice property. You can compute the distance between Bezier curves analytically using different ways. For example, one is you can just use the maximum of corresponding control points. And this gives us a kind of a systematic way of doing a linear or binary search. You can say that I want to apply a binary search, and I want to make sure that the distance between the actual Bezier curve and the approximation will be less than certain threshold. And then automatically it gives us how many different partitions you need to have. And of course, between linear segments and the quadratic segment, there is a difference because the quadratic segments are more descriptive in describing the local motion, and at the end you get less, such Bezier segment, and it can be something needed in order to, compensate for some computational constraint. And if you want to get a better accuracy, you now have a knob. You can adjust the desired Bezier error, approximation error, and you can get different resolutions of these segments. So the overall story of this discussion about the Bezier curve is they are very effective in terms of motion representation. The convex hull property is very relevant for safety verification, and you can systematically decompose them and verify the collisions at the accuracy level you desire. So this brings me to the conclusion for today's talk. So from my perspective, there's still an open challenge. We don't have an informative safety certificate that does all of the 3 requirements I mentioned. So being able to capture the local environment geometry as effective as possible, we can do it maybe alone, but not with others, like being strongly aligned with the robot motion, or systematically offering a trade-off between the accuracy and efficiency. So I think that this is a kind of a fundamental challenge. If we can come up with such safety certificate, motion planning will become much more easier and much more effective. And of course, the other things are, we have usual non-holonomic system constraints. So a safety certificate aligned with this motion constraint will be more than welcome. Handling uncertainty is a crucial thing, because we have a state estimation uncertainty, perception uncertainty, and safety should be able to, handle these kind of uncertainty properly in the risk assessment. And finally, when I think about the robot motion design, especially reliable robot motion design, it should combine motion and perception, and safety certificate that will be used in such motion design should also couple robot motion and perception in a systematic way. So with this, I will finish my presentation, and if you have any question, you are very welcome to share your opinion and your questions.